Director for Supply Chain Analytics at the Miscal Lab, and also an associate faculty member of the School of Computer and Science Engineer and the eHealth program. He is currently serves as a co-editor-in-chief of the journal N4 and the flagship journal of the Canadian Operational Research Society. Among his current research projects are big data optimization in supply chain, last mile freight distribution, and warehouse management. Today's presentation is entitled Optimization with Big Data Application to Supply Chain Management. I would like to mention that you can send your question by Zoom Messenger, and Professor Hassini will answer as many as possible in the end of the presentation. With no delay, I leave the floor to the Professor Hassini. Thank you, Professor.
Thank you very much, and thank you, Professor Mhada, for this nice introduction. I would like to apologize to everybody for being late. Partly it's my side of things, and I tried to use another link. And I would also like to thank Professor Yusuf bin Addada for his organizing this conference and being very patient with me, especially sometimes with this COVID, and I have a very busy schedule with administration here in the university, and really appreciate the opportunity to be able to present some of my work with my colleagues to you. And I hope there will be another opportunity to do this in person in Morocco. And I have visited before, and it's a nice place to be there and to see people very nice. Thank you again. And without due delay, I will start, and I'll try to be quick so that you can go back to schedule in the conference. So this presentation is maybe a little bit unusual in that I'm grouping several of our research work. And I do work here in McMaster with different schools. So I'm associated with the School of Business. That's where my main position is. And then with the CSE, which stands for Computational Science and Engineering. And I wanted to mention this just to show that some of the research really needs collaboration with more than one discipline. It's not just business. There is computer science, engineering, civil engineering. We work with people in that area, in math and statistics. And eHealth, it's a program that has with health science here, the Faculty of Medicine. And we have had some infrastructure on a big data lab that we refer to as MyScan for marketing and supply chain analytics. And that's where most of this research is being conducted, where the actual servers sit and the software associated with them. I would also quickly acknowledge my co-authors here, Srinivas Tamvada, who's a PhD student who just finished this summer, defended his PhD thesis. Part of the big data and Spark Hadoop type of computations he's really responsible for. Just got a position with Penn State University, and because of COVID, it has been delayed. My colleague here, Manish Verma at McMaster University, who works more on transportation and network design. One of the discussion will be related to that. And Bahara Mansouri, who was one of my PhD students in computational science and engineering, now at another university here in Canada, St. Mary's University. Nader Azad, who was a postdoc with me for some time at an Ontario Tech University here. And Edward Klotz, who used to work with IBM not long, maybe the last few months, has moved to Gurubi, which, as you know, IBM has marked CPLEX for mixed integer programs, and Gurubi is a competitor. Edward Klotz has been very helpful with giving us some insight into how CPLEX works from the inside and how we can make use of that knowledge to couple CPLEX with big data technology. And I'll talk about that especially in my last few slides. So I'll go quickly here, but please, if you stop me if there is any issue. So I'm not sure if this is blocked here, but the title may not be clear. So I'll start quickly with a definition of what is analytics and what is big data and why are we interested in that. This is very generic knowledge, and I apologize if some of you are already familiar, but I always want to make sure that when we mention concepts and we talk about things that we have a common understanding. So at least I'll tell you the way I see these things. And you will note, some of you who are familiar with some of the techniques like decomposition, and that this is not entirely new. I call it more of a progressive type of research, that we're taking some of the existing knowledge but adapting it to the situation we have with this big data and the interest, especially from industry, in big data technology in the last few years. So analytics, I think a lot in industry, and now more and more in textbooks, the new generation of textbooks in decision analysis or optimization or business analytics, they do classify it into 3 segments. So there is descriptive analytics, which essentially manipulates data, looks at data, and try to see what is happening. It could be instigated by an issue in the company or whatever we're studying, or it could be just analysts looking at the data and trying to find some insight from the data. And increasingly, this is happening in companies because some of them have invested a lot in big data technology, like data centers or renting servers from companies like Amazon, Google, or Microsoft. And they want to get some return on that investment. And so sometimes an analyst will have a defined project. Other times they would be told, okay, look at our data in the company and try to see what's happening and if there is any insight that can help us improve things. So that in terms of tools, what do we use here? It's mostly visualization, graphics, and simple statistics. Then we get to maybe a little more sophisticated level of analytics, which is predictive analytics. And I think this is where a lot of the interest is happening now, both in academia and business. And this is where we try to predict the future. Again, the concept is not new. We have been doing forecasting in operations management, in industrial engineering, systems engineering for a very long time, and even marketing, economics, etc. But nowadays it's combined with more interesting applications of machine learning, artificial intelligence, deep learning, and the idea that you can combine different types of data, not just structured data. It could be text, video, sound, etc. And you try to get insight, and it has to be done in a competitive way. And that's the definition that I will focus on when I go through my big data analytics definition. And then prescriptive is where we use more formal, sophisticated, I would call it, tools. So this is where our area, operations management, operations research, management science, these fields really play a role, is in this level of predictive and prescriptive. This is where we use either optimization or maybe simulation, where we tell the decision makers, this is the best recourse of action, depending on what we have found in the descriptive, predictive stages. So if we're thinking about supply chain management, because that's my focus and that's really where a lot of my research is, optimization applied in supply chain management, the interest of big data is driven mostly by the industry. And so we would look at some sales data or some production data. That's our descriptive, try to have graphs and analyze that data. We may use predictive modeling to find potential demand, or if we're looking at the production side, maybe predicting failure or issues with delays in shipping. And then prescriptive, that's where we develop more sophisticated optimization and simulation models to look at maybe find the best plan to do production or the best plan to distribute or ship. So I like to use also this framework that has been suggested many years ago by SAS Institute, and this is an institute that's associated with the North Carolina State University, and they're being driven by academics, and they do some, I think, serious research on the advanced statistics side, and they're now some of the big players in this space. And so what they put 8 stages, and I usually like to use this in my courses and also in discussions within our faculty with the dean to argue that our field should be one of the main drivers of business analytics or data analytics or data science, data engineering. There are so many names now, and there's slight differences in industry for each one. But that's the trend now, at least in some of the universities I'm familiar with, that the operations research management science field owns these type of, in terms of programming in universities. And because when we look at what's happening here, there's the lower stages, these in black here, business intelligence. So preparing standard reports like on production quarterly or month or annually, and then digging down a little bit, some ad hoc reports, maybe want to look at a certain production station or a certain product, and then we want to find where is exactly the problem. That's where we go and dig more deeper into where the complaint is coming from, whether it's production or distribution side from our customers. And then we want to find maybe issue alerts to the managers or to our customers in terms of where problems may happen or where actions could be taken. So this is not new. This is really business intelligence, and some companies like Microsoft, they now offer solutions that are compiling all these different options. And then this is where maybe more the advanced type of analytics happens, which is more referred to as business analytics. And here too, it's not completely new. The only thing that changed is the type of data, the amount of data, the large of data, and some other properties related to the data, which I'll talk about soon after. So statistical analysis to find maybe it could be as simple as regression analysis, and then forecasting, which I said is very well known in our field, but it could be now maybe using more sophisticated techniques, especially at the level of prediction of what will happen next. Here it's more traditional trends like the using Holt's or Winter's method, those who are familiar with operations management type of forecasting techniques. And then here it's more sophisticated machine learning, like vector support machines or decision trees, or other classification, supervised and unsupervised techniques under machine learning. And then optimization, which is put at the top there. And given my field is optimization, you will guess that's why I like this, using this graph, because I think it gives some merit to the value of optimization in businesses. And I do use this a lot to argue for why we need to train our students in those techniques. And I have observed recently, the last maybe 10 years or so, many of the companies that wouldn't have hired somebody to just do optimization in retail in particular, they're hiring people and they're telling them, okay, we want you to develop models with CPLEX, for example, and solve some of the issues. So there is much more interest now at this level of optimization. It used to be there. It used to be more some specific firms like in airlines and maybe some others, big firms. Now it is more common and it's seen more as a competitive advantage. So that's just briefly what is happening on that space. So I'll see if I can move this. Okay, yeah, good. I can move it to the other side. So hopefully this is more clear. And please stop me if there is any question, because I tend to be very quick here. So the definition of big data analytics, I'm sure many of you have heard of the 3 V's. And it's typically understood to be volumes, that the data is very large, variety, that it has different formats, text, video, sound, etc., and velocity, that is coming almost close to real time. a lot of data, but I added a few other things here. And I think from a business perspective, this is important that we emphasize economically there, extract value. So if you go to a company and say, okay, let's get a lot of data and let's get it from different sources, and let's get it very quickly, and then you don't do anything with it. And some companies at some point in time, they ended up there. They saw the drive for investing in cloud computing, buying servers, collecting every data you can, putting sensors in different places. And then what's the point? Then what do you do with it? Quickly, the people who are in higher management started asking questions. You know, in business, if you invest, you expect some returns. So what do we do with it? So that's where I thought it is important to put some value, that you will have to extract some value. And that's really what our field helps with. And then also veracity. This is important, especially in the social media world, where we see a lot of data is being generated there. And there are a lot of concerns about the authenticity of that data, and that sometimes there are fake companies or players who put information there to deceive or impact decisions. The elections, especially in the US, and it's happening now, is usually a big theme, but it's also happening with companies that may hire people to advertise their products and try to push it, even with online reviews for companies like Amazon, with millions of online reviews. And the authenticity of how good are those reviews or how real they are is important. So it's not only good to have big data, but it has to be also, the veracity has to be verified. Okay, so let me just make sure I'm on this screen. I mentioned when I started that I'm associated with different programs, and it's not just to say I'm in those programs. I think I wanted to make the point that interdisciplinarity to work in this field is becoming more and more important. And one way of looking at this field is there is computer science in terms of dealing with data and database management in general, and programming. So using languages like now that are very common in this field, Python, R, Hadoop, Spark for big data, specific big data solutions, and a lot of other things around them. And then, of course, our field is modeling algorithms, computational algorithms, designing an algorithm, studying its structure, and then testing it, and the statistics related with that, advanced statistics. So those are required. And then there is the business, what I call the business domain expert, because if I want to apply something in retail, I have to have some idea about retail sector. In healthcare, I have to have some idea about healthcare. And that's where we may need to interact with people who know that domain much better. We may have the tools, but not the domain expertise. And this is also, I wanted to put it here because I understand most of the audience in this conference is academics, and a lot of business schools, engineering schools, science faculties, they are have already started programs or thinking about starting programs, reviewing their programs. And I think one of the challenge we have in many places is dealing with this interdisciplinarity. And so you may find people, they are very good in coding, but not that good in modeling, and vice versa. And so that there is a need to think about how to, from first year, whether it's undergrad or master's, PhD, how to train students properly in these different tools. And in between, I tried to put some of the what is usually done within big data. Here we have what if scenarios that typically involve looking at the business situation and then using more statistics type of tools. There's data mining that uses some of the specific, or it could be either text or data mining, to look more deeply, in a more structured way into the data. And then there is simulation and risk, and that's where the higher level of analytics, and in between, visualization is becoming so important. And I think in our fields, we just take it for granted that students will come up with their own visualization, etc. But it's something important to think about incorporating, and there are leaders now, like Tableau is one of the software that's leading in that space, but also using R and Python. They have a lot of sophisticated packages for visualization. And I see now more and more textbooks are talking about these topics, and we even have courses now that almost spend either maybe a third of a course on visualization, and there are some computer science graphics visualization courses that also look at that. So that's becoming an important area. In a business context, and I interact a lot with the students that I supervise when they go into industry, it's becoming almost critical that you do a project and then management is expected that you will generate one slide with your all your data, your graphics, your insight in that one slide. Could be animated, but that's a trend. Some they call it infographics, etc. So there's lots there. Some of it is led by industry, some is classical. And how do you design good visualization based on your purpose in the project? Okay, so why now the interest in big data? I think it has been growing through time, but what happened during the last few years is the data availability shot up very high. We have a lot of data available now, thanks to mostly these small devices and Internet of Things and sensors that keep sending, like smartphones are one, and the social media. So that is helping to the spread of data, and I'll give quickly some examples. And our ability to process that data has been much slower. It's growing, but it's much slower. So there is a gap, and that's where there is a lot of interest in how to address this issue. You have a lot of data, you want to make some insight from it, how to do that. And many companies are investing a lot in that issue, including researchers in universities too. So here I just put some to give perspective, and this is coming from SAP, the Enterprise Resource Planning System, which we have some partnership with in our school. So we use it in some of our courses, and we do take some of their open courses. So some of this information is coming through that. Just to give you an insight about the size of data we're talking about. So if we're thinking about transactional data, more sales data and ordering data, it's in the terabyte size for big companies, like 10 to the 12 in terms of the bytes. And for online processing data, it's tens to hundreds of terabytes. So it's in that range. And then when we talk about big data, it's in the size of 10 to the power of 15 petabytes, it's referred to. The world of IoT data, Internet of Things data, is even more. We think about exabytes, and sometimes maybe people will say 10 to the 18, that's an exaggeration. We don't really have this data. It is not difficult to imagine that, especially, for example, in the auto sector, if you think about how many cars we have, how long they spend their lifetime, suppose 10 years, and then the computerized and these GPS systems in the modern cars that we have, and the messages that they intercept, they send. And if you think about all of that and that network of signals in and out of cars, we can calculate that it could be easily in the exabytes. So quickly you see that these car manufacturers, the car dealers, the insurance companies, they could have access to a lot of data. And some of the companies here, like Ford, they are already doing some of that, and they're working with some insurance companies, for example, to track the behavior of drivers when you're going into an intersection and it's red light. What do you do? Do you slow down? Do you just take a sharp turn? Those kind of things. And some of them, they also add a device that they put in the car with the agreement of the driver. So in addition to the computerized system that comes in the car. So that's one example that shows that we are already there. This is not imaginary. And then the Internet of Things. So I have done some more research on that area, more on really conceptual, so not working with the actual sensors, but that's a big area. I think it will be impacting our field in terms of supply chain, and maybe revisiting some of the models we have based on the capability that these will provide. And so there are estimates that now around us, there may be around 12.5 exabytes per year generated by those devices, including smartphones. Okay, so I'll just maybe go quickly here. There's some data on, this is mostly North America, on huge demand for big data economy, hiring people in this area. And I think what I have seen recently is companies like Sony, Caterpillar, and these big players, they're hiring even people who have the potential to work in this field, because we don't yet have full-fledged programs, graduate programs that graduate people with these skills. We just recently had few, they're starting. And so they would hire a mechanical engineer with a PhD or an electrical engineer, and then tool them and get them into that industry. The finance industry is another example. There is a lot, and there's some research that was done into empirically looking at companies that have already invested in big data versus those that haven't, and showed that there is a big difference there. I mentioned graduate programs. In the Canadian context, the funding companies, they're also targeting some of these fields. So CFI had put some big investment into computing in general, but supporting this area. The federal government is also supportive of that. The publishing industry, there are so many journals coming out. This is actually a little old, maybe there are more. And also Informs, the Institute for Operations Research and Management Science, some of you may be familiar with, they have also had some certification called the Certified Analytics Professional. So if you take a certain exam and do some training, you get certified to work in this area. So those, I see them all an indication that this is something serious and changing in this world of big data. So now back to my own interest. As I said, my background is in optimization, so I'm really coming at this from that angle. And what we try to do is to focus on the area of, when we have big data, what does it mean for optimization? And maybe I'll give you in brief, because I know we're getting very close here. So one issue is how can optimization benefit from big data? And on the other side, how optimization can benefit big data. And I have started a course 2 years ago for our PhD students on this topic in particular, which I call Big Data and Machine Optimization and Machine Learning with Big Data. And how can machine learning benefit from optimization, and how optimization can benefit from machine learning in the context of dealing with big data. Okay, so I'll skip these, I just summarized. And the two applications, there's some, so it's not really all qualitative, there's some math, but I think I will just go quickly to some of the applications that we have done. So one of the applications we have done, maybe I'll go back to this chart where it shows the algorithm, is with big data and optimization, is we worked on some auction design mechanism for large marketplaces, places that could be online, that could be for the automotive, or in contexts like eBay, and where you have consumers all around the world that could participate, where it generates huge problems. And how can we solve that? So at the basis, that problem is very simple. There are two versions called the winner determination problem, and mathematically it's not that sophisticated. And there is another version where we impose that one bidder in the auction will serve one order. And if we remove that, the problem becomes simpler. There is lots of literature on this problem in a traditional context. We have focused more on when we have more, we're dealing with large scale data. And we used a technique that's also well known, Lagrangian relaxation. and proved some results. For example, here the equivalence of Lagrangian and really linear relaxation, and that helped make the job of solving those large problems much easier, because we move from mixed integer programs to linear programs, and we can scale up much more easily in terms of time and efficiency of the solver. The idea also that we used here, which is not new, but it was creative in this context, is that we're not using Lagrangian relaxation only as a solution technique. We have also used it to provide a proxy for the multipliers. What kind so the Lagrange multipliers themselves will give to the auctioneer an insight about the pricing, the optimal pricing in the auction. So that's one application, and I actually had them here in the top here, but I don't know why this screen is not all entirely visible. So the second topic was on another big data application in supply chains for design of reliable supply chains. And I will just maybe use this diagram to talk about it, and then the technique, and skip to the next one. So if you consider this side figure A, we have a normally functioning supply chain where customers are being served from facilities, and then there may be a disruption. And nowadays we hear of disruptions a lot, not just the pandemic, but even before that, tsunami in Japan and other issues could disrupt supply chains. And we did actually, one of the applications, we applied it to the Toyota supply chain itself, and looked at the impact on that. So here there could be disruptions and mitigation strategies, maybe reallocation of inventory from one facility to the other, maybe losing some of the demand because we can't afford to have it, or subcontracting to a competitor to satisfy some of our customers' demand so we don't lose them. So that was the context of this application. And again, we resorted to the old known techniques of decomposition. We used Bender's decomposition in this case. Frankly, one reason for using these techniques is it's easier to publish in reasonably good journals, because if we just use heuristics on other techniques, they may not appreciate the work as much as if we use some known model. So we talk here, we also came up with some accelerated constraints for Bender's. And then the last one, this is, I would say, is the most maybe related to the big data technology. So this is what Srinivas Tamvada, one of my PhD students, worked on. And this is distributing branch and bound using Hadoop Spark technology. And I have it here in my slide up there. It's called SparkPlex. So we came with the name for this solver, Spark, in reference to that technology, and Plex in reference to CPlex. And that's why Ed Klotz was helpful, that we had that discussion with IBM about how that can be done. And at that time, when we started this, maybe 4 or 5 years ago, there wasn't a lot of noise around using Spark. In fact, we started with Hadoop. That's why I put there, and then we moved to that. And so these are some of why we focused on those: the distributed file system feature of Hadoop and Spark, and the Spark dealing with real data. And this was actually the reason we got in here was motivated by an industrial problem that we tried to solve, and we couldn't even input the data into CPlex. It was huge, and that problem also had real-time updates that could be text messages or emails that CPlex wouldn't handle immediately. And so that's where we thought, okay, this technology with big data and the idea that it deals with any data you send it to, it has the framework for dealing with different data formats, why not use it? So that's where it came from. And we tried to combine the good features of Spark, that it is really made for dealing with big data platforms, and CPlex, which is one of the leading solvers in the industry for mixed integer programs. The problem we were dealing with was a mixed integer problem. And one of the ideas why we call it distributed branch and bound is very simple, is if you have you're doing a branch and bound tree and you have some nodes, there one of the options is to distribute them to different clusters or different computers and solve them using the distributed computing platform. This is also not new. What's new in it is we're using the big data platform to do that rather than old technology. This is the industrial problem, and it's a little bit unique in that we're dealing with a reverse flow, not forward flow. So we're dealing with a big national retailer that has hundreds of stores, and some of its obsolete inventory has to go back in the supply chain. We call the reverse product flow. Some may be redistributed and some may go back to the vendors with some percentage rebate given back to the retailer. And this is, here we talk about how the products flow back, and here we talk about the cost. We came up with a mixed integer program. This is the case where CPLEX had big challenges solving it, and so we paired it with Spark, and we tested it on that context. And this is really the wishes of the company and the research team that worked on this. Is we want solutions very quickly, possibly help with negotiation, and then also support sales in terms of compliance with the contracts. So we came up with an MIP, used CPLEX, and currently what they're using is decomposition and heuristics. We tried the SparkPlex. So very promising solutions on that industry problem, but also we are doing tests now with some open known MIP lib problems on the web, publicly known. This is one of them, one of those problems. And as an example, with SparkPlex, it solves in about 45 minutes using simulated machines. So we simulate them on some servers in the lab, and standard CPLEX would take more than 4 hours. So there's a huge potential for savings. And when we discussed this with Ed Klotz, he was very happy with the performance, and we are in discussion. I've said here there are some other problems very more challenging that CPLEX will take days, and SparkPlex would solve in a very short time, in minutes in some cases. So what we're doing now is testing on real clusters, both in the lab but also with some industrial partner. And we're looking at another application is learning to optimize, where we could use machine learning to help with the optimization, but at the same time to also learn the algorithm and improve the algorithm in the optimization context. But at the same time also optimize we help the machine learning optimization procedure itself. And this is the idea of that optimization helps machine learning and vice versa. Machine learning too can help optimization in the context, for example, of predicting the length of a search tree in branch and bound, or predicting which branch will lead to more promising, quicker solutions, etc. And there are already many people working in this area. So I'm sorry to be very quick, but if you have any questions, please let me know, and I'll be happy to share the slides. And if there is any follow-up by email, please feel free to email me too. So I'll stop here.
Thank you, Professor Khelfi Hassini, for this interesting topic. Now let's go to question. You can have like 10 minutes question. You can, vous pouvez activer le micro et demander, sinon vous pouvez lever la main.
J'ai une question.
Okay.
Yeah.
Thank you for this presentation. I want to know what exactly the difference between predictive modeling and forecasting.
Yeah, so I think that's a good question. And, you know, there was a joke in the internet or somewhere, I saw it in some email sent to me, that in the 1980s, y is equal to ax plus b is called linear regression. Now we call it machine learning. So some people think that most of what is in this field is really rehashing of old things. I think it's not entirely that. There's a lot truth to that. back to the question of difference between forecasting and prediction, I think at least from the industry side, when they talk about forecast, you are looking at a trend to say what would be my demand next month, or how the trend will be. Is it increasing or decreasing? When you expect that demand will drop down? So that those type of questions regarding to forecast. And there are some traditional techniques for using that. When it comes to machine learning, it is a little more or prediction, which uses more sophisticated machine learning. At the base of it, you could use linear regression. So most machine learning books, they start with linear regression, which is really, in the forecasting context, it's the linear trend, and some call it Holt's method when you use exponential smoothing. So there is some intersection. I would say predictive modeling is more comprehensive than just forecasting, at least in the traditional sense. That forecasting in the traditional sense has certain techniques, mostly focusing on trend, what will be the trend in the future. With predictive modeling, there is it looks more at clustering, classification, and other questions that one would want to look at. For example, if we want to see, we have our customers and we want to divide them into different clusters depending on certain measure, that would be more under predictive modeling than forecasting.
Okay. Yasmina Saghir, you are next. Yasmina? No. Another question?
Please, Madam Fatima, I have a
Okay.
question.
Go.
Okay. Thank you for your conference. It's very interesting for us as the specialists in supply chain management. As it was proved in many research, big data has high potential for improving efficiency and effectiveness of producing, and has many benefits. But in another way, it was proved that big data is often outdated or incomplete. This can affect the time that can be used for innovation. How can we prove that big data is always is a strong way to improve supply chain management? The main problem in supply chain management is always the time. Okay.
Yeah, thank you very much. I think that's also a great question. There are a lot of people are looking at how big data could be beneficial to supply chains, and looking at a more strategic level, for example, what kind of strategy the company should have, and to the operational level in terms of how big data is being used to improve. So I saw a study, unfortunately I forgot the author name, somebody in MIT has shown that 5 to 6% improvement in productivity in general, which is very attractive as a percentage, because there aren't many other investments that would give you that kind of improvement in productivity. There are also, so for example, in terms of time, yes, time is critical, and how some companies are using these big data tools, especially those who have the data, like Amazon, for example, to be ready for what may be the demand in the next week or so, but also to optimize the last mile in terms of distribution. And so I've seen or heard from analysts working with Amazon that work on predictive models to that as a subscriber of Amazon, as you log in into the website, and after few clicks, they have an algorithm that starts modeling what you will be buying, very likely what you will be buying. And sometimes they are so accurate that before the person puts the item in the shopping bag and presses on order, the item would have been already picked from the warehouse shelf, put on a conveyor all the way to the station. They're so good and so confident in their prediction. And that's part of minimizing the picking time and what happens inside the warehouse, but also their promise of getting things quicker, either same day or next day. So it's helping in that regard. And I think Amazon is one of the good cases because they have the data to do it. And they have that advantage in terms of other players in that distribution and supply chain management, the last mile of the supply chain. I think that's where I see a lot of applications of big data now. Some people are dividing now the supply chain into last mile, which is more these e-commerce deliveries, and seem to be growing a lot now with pandemic because people are afraid to go shopping. So they're ordering more and more online, especially in North America. And there is the middle mile and the first mile. So the first mile is typically getting things into the country or getting things from a manufacturer, and the middle mile is where a lot of the decision of transportations happen. Maybe I would say less applications of big data on the first mile, middle mile. A lot is happening on the last mile because there is a lot of technology also being used there. Some companies using things like automated vehicles and robots within warehouses with sensors, drones, and I think that's where a lot of data is happening and the potential of big data applications.
Other question? If not, we can close the session, but before I want to thank again Professor Hassini for this interesting topic and for this presentation and for your contribution to GOV. I also remind the audience that after this session, we have 2 parallel sessions. So you are welcome to go there. Thanks.
Thank you very much, and thank you for the great questions, and wish you the best with the remainder of the conference, and I hope everybody stays safe and healthy. Thank you very much.
Thank you.